Thank you very much for the introduction. And I would like to thank the organizer for inviting me to speak on this topic. And today I'm going to talk about the residually indistinguishable case of Ribet method for GL2. And this is following the talk of Schmidt in the morning, where he gives an introduction on the residually distinguishable case of GL2. And I want to say that I'm super honored to present this part of the recent progress for Hilbert 12 problem, which is pioneered by Shomit and Mahesh. And I'm sure that it will be better for Shomit to present this part and speak for himself, as you are really the one who make crucial progresses towards this problem, but I'm very happy to describe this theorem as a non-expert on Blumer-Stark, as I hope to convey the idea that this is a theorem that is readily accessible to general number series, and although the direct consequences of this is mostly for p equals 2 for the relevant questions, and it easily scare people away for that reason. I think it should not be considered as a technical improvement towards a very specific problem, but rather it is an independent result which is probably of interest to a wider audience in number theory. And the idea of the proof actually simplifies things significantly instead of complicating things. So so to start the talk, the story start from Ribet theorem, which is a converse of the Herbrand theorem. So let P be an odd number, odd prime number, K is even, integer between 2 and P minus 3. So we look at the number field that is Q joining P's root of unity, and let C be the P part of its class group. So this is an algebraic object, and we also have the analytic object, which is the Bernoulli number. Then it is a Kummer theorem that you can actually find a connection between the algebraic object and analytic object, that if the class group is non-trivial, the P part is non-trivial if and only if the P divides the Bernoulli number for certain K listed here. And Herbrand gives the refinement of Kummer theorem by taking into consideration the Galois module structure of the class group. So i.e. we consider the Galois group of the cyclotomic extension acting on the class group, and then C naturally decomposes as a direct sum into component that is indexed by omega to the I, where omega is this Cashmuller character. And then the theorem says that for even K, which correspond to the minus part of the class group, the class group, the component is non-zero, implies that P divides the Bernoulli number with that index K. And so the theorem uses Stickelberger's ideal, which is gives the first case of the Blumer-Stark when the base field is Q, and Ribet theorem give a converse of this theorem. It says this is actually if and only if result, and the idea is via this loop of that you have already seen in the morning talk by Shomit. So this hexagon with 6 nodes, each of which is a big object, big topic in number theory. And it has been used in other contexts, proving important results. For example, it has been used by Maser-Wells to prove main conjecture of Iwasawa theory over Q for P, and later on by Wells to prove main conjecture of Iwasawa theory over general totally real fields, again at P not equals to 2, and by Skinner-Urban to prove Iwasawa main conjecture for the curves, and most recently by Schmidt and Mahesh to prove Boomer-Stark conjecture, again away from P equals 2. So what are these this loop? Basically, to prove the direction in Ribet theorem, we usually start with some analytic information like the Boolean number or some special value of L functions, and then construct some Galois representations using the Eisenstein series. And now with the Galois representation in hand, we can extract algebraic informations to show something non-trivial about the algebraic object on the other side of this problem. So usually the question is to show that the algebraic object is big so that you can prove the direction where the analytic side implies the algebraic side. And the particular node that I'm primarily going to focus on today is starting from the Galois representation to the Binet extension of the cyclotomic field. So this result that we are going to show today is going to have the power that you can eliminate P not equal to 2 assumption for many of these results. For example, the main conjecture of Iwasawa theory over general totally real field, and the Boomer-Stark conjecture over totally real field. So now let's be more concrete. So what do we mean by going from the node of the Galois representation to the abelian extensions, or some equivalently some one cocycle? So usually we will obtain a Galois representation from previous steps, and you get a group homomorphism from your compact absolute Galois group to GL2 of K, where K is a total ring of fractions for some local ring. And usually the representation is irreducible in suitable sense. And importantly, we will get some approximate information on the characteristic polynomial. And the general question now is, given this representation, how can we extract some relative abelian extensions from rho? Or in other words, how to construct some Galois module with a particular cocycle so that give you a certain abelian extension-like object. And moreover, once you have the Galois module, how do you show that the module is large enough? So I want to say that usually these Galois representation we obtain also come with more information on what is the behavior when you restrict the rho to decomposition group or inertia group. And to focus on the topic today, luckily these does not add too much difficulty to the core idea or proof. So we will just set aside the discussion for now. Let's look at a first example. And this is the exact setup in Ribet original paper. So in his case, the T is just the ZP and K is QP. And the character, the two characters that approximate the eigenvalues is the trivial character and the Tetramuller character raised to certain power. And then the Galois representation is giving you a continuous homomorphism from GQ to GL to QP. And because GQ is compact and the rho is continuous, we can actually find a good model of this representation so that all the image of the GQ lies in GL2 of ZP. And then from the Brouwer-Nesbit theorem, it tells us that the semi-simplification of this representation is just determined by these two eigencharacters. Therefore, we can further conjugate so that the image of the Galois representation looks like exactly the chi1, chi2 on the diagonal and the 0 in the lower left corner. So now you can form, you can look at just this representation mod P, and this is what we call the residual representation, and it cut out, so it is a representation, it is a map from GQ to a finite group, and it cut out a relative abelian extension over a number field, which is fixed by the kernel of chi1 and chi2, which is just the Q John mu P in this in Ribet original case. So this tells us some okay, so this, at least we construct some relative abelian extensions from this scalar representation. Or if you would prefer to use the language of cycles, cocycles, you can let the module to be generated by the right upper corner, this B component in the matrix, and then it will be a G module where the action is easily seen from looking at the conjugation action of the image of GQ. And the B component, just by doing the matrix multiplication directly, the B component has this congruence relation mod P. So by multiplying both sides with chi1, chi2 inverse, then you can actually see that this give you a G module with action chi1, chi2 inverse, and the kappa that maps sigma to B of sigma, chi2 inverse of sigma is well-defined one cocycle. And now this finishes the first task, which is you want to construct some algebraic object. And then the next task is you need to show that this algebraic object is large. So in order to show that this cocycle is non-trivial, and we can just follow the original argument of Ribet in his paper. Now, suppose this is Zo1 is a Galois representation you get from the previous argument, which just have this particular format, then its matrix coefficient, this matrix entries satisfy those congruence condition mod P, and suppose this kappa is a trivial cocycle, then that means you can find the X1, so it is lying in B1, and equivalently, this give you an expression of the B1 entry in this Galois representation. Now, if Now, since we have this x1 in hand, you can construct this matrix 1x1 0 pi, where pi is the uniformizer of ZP. And by conjugating row 1, you can find another representation where now the entries satisfy a higher congruence for this left corner. So you can repeat this process until you can find a cocycle that is non-trivial. And if you never find a non-trivial cocycle, then you can actually construct this element little x, that is x1 plus pi times x2 plus extra, and then conjugating the Galois representation of row 1 using this special element x will give you a reducible representation. And that is contradicting the irreducible assumption we start with for the Galois representation inside ZP. So the remark is that this argument can be generalized to DVR whenever T is a DVR, and the two important places where we use DVR is that before we access any information of this representation, as long as we know that GQ is compact and the row is continuous, then just knowing that the maximal compact subgroups of GL2K are precisely those GL2 of T, we are guaranteed to find a model for this representation with T coefficient. And a second important point is that for a DVR, we can actually use the uniformizer, which is the generator of the maximal ideal, to construct these matrices to make the conjugation. And that's why these arguments cannot be readily generalized to general T. So now, why for all these previous mentioned results, we have assumed P not equal to 2. And this is something Shomit has talked about in the morning. This is a residually distinguishable case. So for general T, it is useful to notice that we are not guaranteed to find a good model in GL2T. And for example, the T Hack algebra can actually come up as some local ring that looks like, oops, that looks like some subring of Z2 cross Z2, and by this congruence condition. So firstly, it is easy to notice that it is not a DVR because it is not even an integral domain. For example, you can use 2, 0 times 0, 2, and this is going to be 0. So you have 0 divisors, and at the same time, the maximal ideal, which is just the element that are even entries for both component, it is not a principal ideal. So you cannot find a uniformizer. And the total ring of fractions is Q2 cross Q2. And that's why you can see you cannot always get a model inside the GL2T because you can easily define some other T local rings that is even having higher congruences and arbitrarily high congruences, but the total ring of fractions stays the same. So we don't have a good model at first place. But if we know more information, say if we know that chi1 and chi2 are not congruent mod the maximal ideal, then we can take advantage of this and choose some basis that is particularly nice. So you can start with some tau and where chi1 and chi2 are not congruent at tau, and use that use the eigenvector for tau to find a good basis of this representation, such that such that the row of tau exactly look like this expression mod the ideal. Okay, I should have put it well, maximum ideal, good for now. So then observing that doing the matrix multiplication for a general row of sigma and together with this row of tau, you can get the two equations that Shomit did the calculation this morning. And it is because chi1 and chi2 are not congruent at tau, this linear system is invertible mod M. Therefore, you can actually solve A and D back and prove that even though we do not have B and C readily in T, you can find a basis where A and D are in T. So the situation is slightly worse, but not too worse. And then you still have the multiplication give you this congruence for the B coefficient. This means that now you can again define the T module that is just M mod IM, where M is, okay, sorry. I wanted to somehow change. Yeah, it should be this. Has a similar Galois action, and you can also define the cocycle in a similar way. And I wouldn't spend more time on this part showing the largeness, as Shomit has already did it in the morning, but essentially follow from that being the row being irreducible again. And the reason, to conclude, the reason that we need P not equal to 2 is that the characters that we need to deal with or satisfy the non-congruous mod P at complex conjugation. But this is not the case at P equals 2. So we need some new idea at P equals to 2. And this is what we call the residually indistinguishable case. And our main theorem now states that for a general complete reduced Noetherian local ring, and I is an ideal, G is a compact group. Suppose you have this Galois representation with the K, that is a total ring of fractions, and characteristic polynomials lying in T bracket X, and having this congruent condition mod I. So suppose rho is irreducible for each to each projection to the field factors, then we have a finite generated T module. So similarly, again, just like what Shomit need to modify in the morning, that we also need to assume that the map of the group ring into the 2x2 matrices is finite generated, then there exists a finite generated T module M and a cocycle in Kaba with the condition that the fitting ideal of the module is contained in I. So as it is being introduced in previous lectures, the fitting ideal of a module measures how large the module is. And the general version of this theorem will discuss rho together with the local conditions and the T possibly being reduced, non-reduced. But the main idea of the proof does not add up too much for this part. So we will just focus on the simplified version. And another comment is that the proof also does not build up too much difficulty if chi1 and chi2 are general characters. So we will assume that chi1 and chi2 are just trivial character for the simplicity in this talk. And on the other hand, just like in Ribet original version, we can restrict the Galois representation to a smaller Galois group where chi1 and chi2 become congruent to 1 mod I, and then we will still obtain this Galois module M with the same fitting ideal. So in that case, it will be a trivial Galois module, a Galois module with trivial Galois action, and the cocycle, therefore, is just the homomorphism from the absolute Galois group to the Galois module, which is the M constructed. And this motivate, because this is a simplified setting, it is motivating us to construct the M from a very canonical way. So remember, if we assume both characters are trivial, and then the Galois module should be trivial, action, and kappa is just the homomorphism from the absolute Galois group to the module M. So since M is abelian, essentially this is just to look at the image of the abelianization of the absolute Galois group. And since we want to construct the T module, we can just take the abelianization of the absolute Galois group tensored with the T. And now it is well known that the abelianization of a group is isomorphic to the augmentation ideal mod augmentation ideal square. And after tensoring T, it will give us the abelianization tensor with T over where all these are over Z. Okay, so now the idea is that starting from this scalar representation we have in hand, we can extend it to a homomorphism on the group ring things. And this group ring homomorphism give us a natural universe to look at the augmentation ideal. And now it is natural to just look at the image of the augmentation ideal mod its square in the 2x2 matrices and constructed, let's just constructed the M to be exactly that image. And then the one cocycle you want to construct is exactly just this row map. It has an obvious benefit that this construction is very natural, and it does not depend on any ad hoc choices on what the basis of the representation should be, and does not need to depend on clever observations of how to do the matrix multiplications. So it is really a very natural thing to do. But on the other hand, it means that we almost make no work for the construction step. So the main challenging problem here is then to show that the algebra object we constructed is big. So that is calculating the fitting ideal. And by definition, if we have module part M and has a generator relator as a T module, then the fitting ideal will just be if this D is a matrix of the relators, and the fitting ideal will just be the ideal generated by all the determinant of R by R submatrices. And recall that our module is just constructed to be some quotient of the augmentation ideal. This gives a canonical way, not canonical, but a very natural way to construct a generator relator for our module M. Suppose the augmentation ideal is generated by R element, rho 1 through rho R. And recall that these rho I are all images of some sigma I minus identity. So now, now the determinant and the trace of these matrices are all going to be 0 mod I. Okay, and so what are the relators? So there are two types of relators here. And one type of relator is what we call the epsilon type. So these are just the linear dependencies of these rho k in M2, these 2x2 matrices of k. And a more interesting type of relator is called the delta type relator. And this is rising up because we know that we mod up by delta to square, so that if we have a product, let's say rho I times 0j, then it should be written as a linear combination of this rho k. So now the task is to compute all possible R by R submatrices of this relator matrix. And it is quite difficult to deal with these submatrices directly, but we know there is another closely related matrix that we can say something. And it is crucial to remember that in all of these results, if you want to show some largeness result, it is crucial to use the irreducibility of the representation. Now, so how do we use that? Let's just write this rho I as some matrices A, B, C, D. And by looking at the B entry, for example, of the rho I times rho J matrix, then you get the equations of these BI among these BIs. And similarly, you get similar equations for all of these A, B, C, D entries. And you can also get relations of this epsilon type. Okay, so what this can give you is a new big matrices. So if you just replace all these delta ij k following these rules, and then you will get a new matrix that is the same dimension with this relator matrix, but every R by R minor is automatically having determinant 0, because that rewriting these in the matrix format, you will see that all the submatrices have the satisfy this d prime times b1 through br equal to 0. And this is true for any choice of b vector. So because of the rho is irreducible, you can always find some non-zero bi, and therefore this tells you that d prime has to be determined 0. So now we can use this to show that our interesting D determinant is contained in I via comparison. So let's now denote this error term E to be the difference of the determinant of D and the determinant of D prime. And the goal is to show that the error term is now containing I, because we have seen this determinant equal to 0. And this is a very interesting computation to do by hand. So I'm going to just present one very small toy case in the case R equals 2. And let's say this is D and this is D prime. Sorry, this is our D prime. This is our D. And to compare these two determinants, you can just first expand all these determinant. And the degree 2, the delta term, the term with delta degree 2 automatically cancel for these two determinants. So you start with terms that has delta degree 1. And now, for example, this is going to be a good term because we know that the trace A1 plus D1 is in our ideal I. And for the next step, to try to see this more, whenever you see this D2 term, you will actually try to, oops, this is not what I want to do. You will actually compensate to get the trace. And now you will see these two terms. So now in the next step, recall that we have the relation between from these multiplication of row i's, then we up to this equivalence, we will get the last expression. So the last expression is going to be very good for us because every expression now is either trace or determinant or delta, which is in T. So we can show that the difference is lying in I. And it is worth mentioning that though we don't have, did not start with all these calculation, assuming anything like A, B, C, D is containing containing K. So even though some term like this contain the trace in it, it is not necessarily a nice term because these A1 here is not necessarily lying in T. So now so what can we see from these small degree calculations is that we have some good news and we have some bad news. And the good news is it works always. It always works for every small R case where we did with hand computation. And the bad news is we do not know how to systematically organize the calculation to know that it must work in every case for arbitrary R. And so at this point, we have done a lot of computations either by hand or by programming. And for example, this is a code that we use to run it on the computer. And it is a very short code, very simple, but it runs very slowly. So for R equals 4, for example, it already runs for 1 week for Magma in 2021. And now, so what is the bottleneck is that these global bases for these ideal computation is very slow. So the point that I show you, this code is, this is exactly showing how we proceed further, this is exactly what we call the formal variables in our paper. So what we mean is that now, starting from this moment, you can completely forget about the Galois representation and forget about your hack algebra and just to do some commutative algebra. So the setup is you have these, so let R0 be the algebra generated, the polynomial ring generated by epsilon I and delta I jk that showing up in the previous relators, and then just take R to be R0 polynomial ring with variable a, b, c, d, where a, b, c, d are just the entries of these row I. Now, we pick some R by R submatrices in the relator matrix. Our key challenge is to show that these error term, which is a very, very long algebraic expression, it must be able to be reduced to be some representation, some expression, just in terms of the relators and some trace and determinant of all possible product of row I. So equivalently, if we mod out these relators called by J, the ideal generated by the relators, then equivalently, we want to show that in the quotient ring R mod J, the image of the error term should be generated by purely trace and determinant. And here, this is the place we get stuck for a long time and actually doubt if this is really the case, whether it can be done. And
so Jiuya,
yes,
this bracket on the bottom line it's really the sub algebra generated
sub-algebra, yes.
over R0. It's not the ideal, right? Yeah. So
right. So I will actually, yeah. So I changed it
R0
in the later
bracket.
slide. Yeah, yeah. Thank you. Let's say this is R0, but even this is not enough. We will also need also needed to be for this AI.
Yeah.
Okay, so so this is the point where we get this for stuck for a long time, and I remember that Shomi very firmly believe this should work because the only thing that we know lying in T are the trace and determinant. So none of these A, B, C, I are necessarily contained in T, but all the trace and determinant are the only thing we know contained in T. And as a fitting ideal, it has to be some element T. So somehow it has to be the case. The final expression should lie in this sub-algebra. Okay, so this is a crucial idea that we should use some more clever idea instead of just pushing the computation. So this is called the matrix invariant theory. And the motivating classical result here is if you look at the polynomial ring generated by all the matrix entries and imagine you have a GL2Z acting on the matrix A, B, C, D via conjugation, then the subring that is invariant under this action is exactly the sub-algebra generated by trace and determinant. So for us, our ring is more complicated, but nevertheless, it still suggests a way out, which is if we just let those sub-algebra generate by trace and determinant of all product row i's and look at its image, in R mod J, then we will, if we can succeed in showing on one hand that this error term is invariant under the GL2 action, and on the other hand, if showing that the invariant, the subring invariant under this action is exactly trace and determinant, then combining these two sides, we will get our result. So that is the rough idea. So just the two small comment related to the previous typo is that from the previous computation, you can see that all these delta term, like the full degree delta term, exactly cancel. So we're guaranteed that our element E bar, when you consider in this ring, it does not have a constant term. So it suffices for us to show that this E bar lying in A bar. Now, so that is the new question, whether we can show these two sub-questions. And now consider this GL2 action on R. Similarly, as before, conjugating on these rho I. For the first task, we can actually show via direct computation that the E bar is invariant under a Borel subgroup. So so it suffices to look at these two actions, and via some computation, we can see that this E bar is invariant under B action. But it is not clear that E bar is invariant under the action of GL2Z. So that is the first side. And the second side is, for the second side, if you notice that this R is just the classical example tensor with R naught, and because R naught is the flat, we can easily obtain a similar result that the invariant of R under GL2Z is A. But we want the more complicated, the similar result for a more complicated quotient ring. And we are stuck here again for a long time. And it turns out that to make both ends meet, it is crucial to use this, what we call the rational homology. So yeah, so the key observation or the key idea is that you should really consider the GL2 and the Borel as some algebraic group instead of just the abstract group. And for an algebraic group G, and we call the rational module is some G module where the action of the algebraic group are all just some rational functions of the matrix entries. So a typical example is exactly the classical result, the example in the classical result we have seen before. And you can do a computation to see actually the action are all rational functions. And when we talk about those rational modules, then we can use the cohomology, the group cohomology in this new category, where the H0, the invariant, should not just the invariant under GL2Z, but the invariant of the matrix of the G action when you look at all the A point for all A. So similarly, this is only left exact, and you can define the all the higher order cohomology in this category to be the right derived functor of the invariant part H0. So the very first important fact that helps us is that this H0, the invariant part, is isomorphic if you look at the G invariant part or the B invariant part. And therefore, this immediately helps us on the first side. And because the invariant part is really the same for I equals 0, and essentially it is saying that all the higher derived functor are going to be the same for if you look at the G cohomology or you look at the B cohomology. So, okay, sorry, here I should really say that all this is really GL2, this is a Brel. I really mean the specific case. So now, what we can do is just to use the B cohomology to study our element E bar. So remember that our goal is to show that E bar is contained in A bar. And this, looking at this short exact sequence, we can associate to our J ideal, and you can derive a long exact sequence where this R fixed by B now we know is isomorphic to R fixed by G, which is just A. And so now our element E bar is lying in R mod J fixed by B. And if we can show it come from an element in R fixed by B, then it is exactly saying that it is containing E bar. So to show that comes from RB, it is equivalent to show that the connecting homomorphism delta E bar is equal to 0 in the H1 of J. And now this is to show the delta of E bar is equal to J, equal to 0 in the H1 of J. This is done via detour to look at another ideal called J prime, which is just a sub-ideal, a subset of J where only take the relators associated to the B entries for your chosen D. And remember that we have done this previous calculation. So actually, for example, in this particular case, you can see that this element is not only lying in J, but also lying in a small ideal. So we can actually show a stronger statement of the error term. And now for, wait. And for J prime ideal, we can actually use a causal complex to get a nice complexes, and we are comparing the homology of J prime and J as rational modules, we can actually use a cascade of the co-cycle argument. This is what we call in the paper to show that the restriction, the embedding of the H1 in the smaller ideal into the H1 of J is always a 0 map. And from that, we can conclude that our E bar element is exactly lying in R mod, is exactly lying in E bar. And that concludes our proof for the residually indistinguishable case. Okay. Yeah, I think I will stop here. And thank you for your attention.
The questions, comment? Yeah, in your definition of rational cohomology, for your H0 functor, I think I might have missed it, but what kind of rings are you allowed to take for A?
Pardon?
What kind of rings are you allowed to take for A?
For all commutative rings A.
Yeah, and then so the GV equals V would be taking place in V tensor A.
Yeah.
Oh, okay. Oh. I'm confused because, like, how do you define a finite?
Yeah, so then you have to go to the place where that makes sense, which is a V tensor A. Any other questions? Yeah.
Where did you say why this cohomology comparison?
Oh, I should really, yeah, I forgot to say this. So Shomit in the next talk, he will he will actually expand this part in his talk for this comparison, which it exactly explains this cascade of cocycle.
I think he's asking
in
about
his talk.
comparing the cohomology, the B cohomology and the G cohomology,
Mhm.
which I can explain if you want, but
Oh, you mean the D
isomorphism, why there's
cohomology and the G
Yeah, this theorem.
cohomology?
Yeah.
Okay, so I think for this part, it is you need to realize that the G when you quotient out by B, in the sense that so it has a bijection to P1. So
Exactly, it's
if
proper.
yeah,
And
so
B is
so it is
affine.
a compact object, and that is essentially the reason.
So there's no morphisms from P1 to the affine space. So no non-constant. Yes, it's constant.
Okay. Oh, I see. So
So this is why it's really important to work with rational cohomology rather than like group cohomology, because obviously like restriction from GL2 of Z to its Borel is not an isomorphism on group cohomology, but it is in the rational cohomology. So that's why it was like really important for us to shift to that. If there are no other questions, let's thank Jiuya again. And we start